Dear fellow coders, welcome to One Little Coder. This is day 9 of Kaggle's 30 Days of Machine Learning Challenge. If you are new here, this channel is for programming tutorials especially focused on data science machine learning. And let's get started. In the last video, yesterday's, we saw about a very quick introduction about machine learning. In this video, we're going to learn about building our first machine learning model, and we'll use a library called scikit-learn. In the next section, we'll also learn about model validation and why it is important, or what kind of things are we going to do. And as usual, all these links will be there in YouTube description. So if you have not signed up for Kaggle Challenge as well, you can do this along with me. So let's get started with the first tutorial. Right click it, open it. This is your first machine learning model, and you have to log into your Kaggle account if you have not logged into before for you to do this thing. So what is the first machine learning model and how are we going to build it? First of all, we need a data set for our machine learning model. Then we need, in the last section, we saw that there is something called training data. So that training data is what we are going to use to train our machine learning model, and then ultimately we'll end up predicting something. So first, let's look at what are we going to do. So if we want to predict something, so basically this is the model, this is the typical language that everybody would follow. Y is equal to mx plus c. So it's basically nothing but a line. So you have multiple dots, so you try to fit in a line. So that is what is model fitting we learned in the last section. Now the same notations would come across. So y is what you are trying to predict, and x is what you are going to use to predict y. So x's are the explanatory variables, y is your response variable or the prediction that you're going to make, like target variable. So now looking at this thing, we can see that if we want x, we need to pick x, like what kind of variables we think can help us in predicting the y variable. To give you an example, let's think about rain. Okay, so if you want to predict whether it will rain tomorrow, then what do you think might be useful for you to predict whether it will rain tomorrow? So one thing you might want to see is whether there is any cyclone, or whether it rained yesterday, and what is the humidity in the air, like what is the density of water drops, all these things. So you can use all these things and then ultimately say, okay, there is let's say 70% chance that it might rain tomorrow. So now what you're predicting is whether it is going to rain or not, or the probability of whether it is going to rain or not, and that is your y. That is your y. And what are you using to predict? What the factors, the variables that you are using to predict whether y, you can predict y, is what? Your x, which is called the explanatory variables, and y is your response variables. There are different names by which this is called. We'll see this slowly. Now getting into the Kaggle tutorial, we can see first we need to find out, we need to prioritize what kind of variables. Whenever we say, it's nothing but columns, variables, dimensions, factors, all these things usually refer to columns in this space. So first we need to pick what are the variables that we need for our machine learning model prediction. So there are two ways to find the variables. One is using our intuition. They're saying intuition, but you can use your business knowledge, you can use your domain knowledge. Imagine like you are in medical field and then there is something that you have to predict. Probably you have inherited some domain knowledge that you can use to predict what is there, like what kind of variables or columns that would help you predict this thing much better. So that is one thing. Second thing is there are certain statistical techniques that you can use to prioritize the variables. So one, you can use your existing knowledge or domain knowledge. Second, you can use statistical techniques to prioritize picking up these variables. For example, to give you a quick example, if two columns are highly correlated, we usually drop one of the columns. Unless there is a good reason, we usually drop. When I say drop, leave out one of the columns and then we go with other columns. So like this, there are certain statistical techniques for us to automatically prioritize the variables. So that is how we pick the variables. Now, first of all, even to begin choosing the variables and column name, we need to know all the columns in the data set. And how do we know all the columns in the data set? It's quite simple. If you remember in the previous section, we started with pandas. So import pandas as PD, and then you have to give the path, the file path where the file is, like the CSV file is, and then you do pandas pd underscore read CSV and then the path. So pandas pd is the alias in which you have imported pandas. This is your file path, and then read underscore CSV. Once you do that, now this object has become a pandas data frame. So this pandas data frame has got an attribute called columns, which will give you all the column names that are available. So remember, like we did in the previous video, we did Melbourne underscore data dot describe. So that gave us summary statistics about the numeric fields or variables. The same way, if you use the method columns, it gives you all the values, the attribute columns, it would give you all the column names. So you get an idea about, okay, if I want to predict the housing price, what kind of things might be helpful for me, whether the number of bedrooms would help, when was the year built, will that help, where is the address, will it help. So we can start thinking what kind of column names might help us. Another important thing before even you get into modeling phases, first doing exploratory data analysis. We are not going to do any of those here in this case. We might do a little bit of description, but generally you should start with exploratory data analysis and then try to understand insights about the data. Like that will give you better understanding about what is happening in the data. So rather than just blindly going and start building the model, it is always important for you to do in exploratory data analysis, EDA, and then try to understand, oh, what would be this column, what is the property of this column, what could be the property of this column, whether some column is correlated with the other column. If we are going to predict price, this is our training data, right? So because this is our training data, we have got the target value price. So if you are going to predict price, do we know what are the columns that are highly correlated with price, or what are the columns that can help us predict price? So there are a lot of questions that you can answer, and then you can also come up with new columns. So instead of using a number, you can probably create a value out of it and then create a new column. So these kind of things are called feature engineering. So because we are calling these columns as also features, we can say that feature engineering is the process in which we might create new columns or new features that might help our model prediction, model fitting, model training process in more efficient. So we can say that model was able to learn more because we had feature engineered, new features we had created. Now, most important thing is, before even that, we have to start, I said, like we have to start looking into the data, EDA. In that process, one of the things that we have to do is we have to check whether there are any missing values. Now, what is missing value? It's quite simple. When we look at the head of the column, so when we look at head, you might actually notice that some columns, or even if you do not do head, so you might notice that some columns in this thing might have null, which means it does not have any data. Imagine somebody has sent an intern to do a survey for about all these houses, like somehow they must have collected the data, right? So probably one house's number of rooms was not available at that time. Probably one house's bathroom detail was not available. Probably the owner, we did not have information about the car at that time. So what would somebody do? They wouldn't put 0 there, probably, because 0 means they don't have any car. Instead of that, because they do not have any data during data collection, the practices that they might follow is they might use null. Null means I don't have information. It's a missing value. I don't have anything. So one of the important things that we need to check before moving into model creation phase is to figure out whether there are missing values. In the future sections, we might learn how to handle missing values, like what do we do when we have missing values, what are the type of missing values. But before that, the simplest option is to drop the data points where we have got missing values. So when I say drop the data points, so columns, we call them columns, we call them features, we call them variables, we call them factors, and the data points, the rows, are usually called as data points. So what we can do is we can drop the rows, drop NA stands for not available, missing value. NA stands for not available. So we can say from this data frame, Melbourne data, dot, the dot notation, and drop NA. So drop everything that is missing value. And another reason why, so I think it's probably good if I just get into edit mode. That might give some more information for me to show you. Let me get into the edit mode. Just start the machine. I can read it. Yes, the machine is getting started. The first step is I'm running the code, and then so you can see that there's a high CPU usage. I've run. So the next thing that I'm going to do is, we can see all the columns. The next thing I'm going to do is head. So it will help me understand the values, the like top 5 rows, or I can do tail as well, tail, and instead of 5 I can say 10. So you can see I've got the suburb detail, I've got the address, I've got the rooms, type, blah blah blah, everything. And you can see missing values, missing values, missing values, missing. So you can see missing values, missing value, missing value. So this is what we are trying to eliminate by doing drop NA. So the main data set, you can see that it has got approximately 13,580 rows. So now what happens when we drop missing values? So let me say melb no NA is equal to Melbourne data dot drop NA, and access is equal to 0. So just saying that the first column should be the access value. So if I do that, and then if I see the shape, you can see we have almost eliminated half of it. This may not be ideal in a lot of cases, but because we do not know how to handle missing values, now we can proceed with this. So if I quickly see the tail, you can see you wouldn't probably see the missing value because the rows that had missing values, we have eliminated that. So that's what we have done. So in this case, I was just building a different data frame, but when we run this cell, we are going to basically override that existing data with after dropping the missing value. So now there are multiple ways for us to get y and x. So I think we have already discussed that we need y, which is going to be our target value, because the formula that we said is y is equal to mx plus c. That notation comes from there. It's not something that we are doing. We are not trying to fit a line, but basically your machine learning process is drawing a decision boundary. So we are trying to say we need y, which is what we are trying to predict, and x, it could be x1, x2, x3. So this is what we are going to use to predict, okay, features, or we call it features. And that's why we said feature engineering is the process of creating new features that are not already available. So now how do we get these? Right? So the easiest way, there are multiple ways to do this thing, but if you look at the pandas course, which we did not cover, but if you want to do it separately, one of the easiest way to do is the dot notation. So anytime you use the data frame, dot the column name, so you would get the value inside this, and you would get it as a series. So now if you look at a pandas data frame, this data frame is like a combination of series. So the single column is like, let's even do that thing, okay. So now what is this type of this? What is this? This is a pandas core.frame data frame, okay. Now when I do like this, what is this? It's a series. So single column is like series, data frame is like combination of series. Just keep that thing in your mind. So when we use dot notation, we are going to get a series, and then okay. So maybe I'll do just one extra thing, which is series. Sorry, why did I do series? When I do like this is another way for me to extract a column, okay. So I can either do dot notation, I can do this thing. So I've done dot notation price, so that is my y, because we are trying to predict the house price. And now we have saved it in y. Like you can use any name here, it doesn't matter, but when you use y, people might already know that, oh, y is my prediction target, that's what I'm going to predict, okay. So now how do we choose the features? How do we find out the columns that we are going to use as explanatory variable to predict this y? And like we discussed before, we can use a business intuition, business knowledge that we have got, and the other method is to use statistical methods. In this case, let's just say like we'll go with few items like number of rooms, the bathroom, the land size, latitude and longitude, where it belongs to. So that might give us some kind of idea. So when we are going to call it Melbourne features. We can call it X, but whatever name you want to call it, you can call it. So here what we are doing is, we have to pay attention. Here we have not extracted the values. We are just saying these are the column names, features that I want. And now we are going to subset it, or we are going to extract only those columns. So if I run this thing, let's run this thing, and if I print this, print. I don't have to use even print because it's a notebook. You would see just this. This is a string list, nothing else. So what I might do is, now we are going to use this data frame and then put this inside this. So now when we do this thing, x dot head, you can see it just has those values. So it basically has only those columns, and that's what this is. So nothing but. So here in this step, no subsetting in the sense like selecting the column is happening. Here it is going to happen, and this is not the only set of columns we have to play with. So after we do the first iteration of the model, we can always come back here and then change the column names and then see if the model improves. All those things we can do. Just for now, we can just go with this. And you might now ask me, why didn't I just do like this? Why didn't I just do like this? Sorry, why didn't I just do like this? It's a good question. So the answer to the question is, it is always one of the Zen of Python principles is it's always good to be explicit than implicit. So if you keep it in a separate line, it might be easier for anybody to come back and then add a column name. So you just don't mess up this code where you are extracting the data. So that's a simple reason. But if you want to reduce the code line, you can do, but this is always the convention. And so now let's look at the summary statistics of summary statistics of our X, which are the features. So basically we see like 6100 rooms, like we have number of bathrooms, land size, and the latitude, longitude, and maximum value number of rooms is 8, number of bathrooms is 8, and approximately you can see our average is around 2 and a 50th percentile is 3. So not much outliers are there. So like we discussed in the initial state, that finding out missing values is one of the important thing. The same way you might also want to figure out whether there are any outliers, so that you have some understanding about how the data distribution looks like. So that would all come in the exploratory data analysis section. So let's look at the head, which we have already done. So we have an idea about how this data looks like. So one of the important thing is, visually checking your data is very important, because sometimes you might assume something, but when you look at the data, it might not be the case. You inside your mind, you might be thinking, oh, probably it's like this, but unless you actually look at the data, you may not know. So to avoid some surprises, it's always better to actually look at the data. So one of the people I like in this domain, Jeremy, who's one of the co-founders of Fast AI, so he always advocates for you to actually visually, using your naked eye, to look at the data. I mean, you can use specs or anything, but yeah, actually to look at the data and then try to understand what is happening with the data. So now that we are clear with our X and Y, our next step is to build model. We are going to build a model. So for this, we are going to use the library called scikit-learn to create the model. One of the reasons I love Python for machine learning is because scikit-learn is like your one-stop solution. It's like, your one app that can do everything for you. So scikit-learn is like the library that can do basically everything for machine learning for you, and you will learn more about it. So the way the library is written is called as sklearn. So like, for example, whatever model you want to do, in this case we are going to use a decision tree regressor. So decision tree is we saw decision tree in the previous example, like the last class. Now maybe before even we jump into this, a very quick introduction to machine learning, I should say. Very poor introduction to machine learning, I should say. So if your target variable, your target variable is what you're trying to predict. If your target variable is a character, it's like a category, yes or no, high, medium, low, that type of machine learning is called classification. If your target variable is a number, it's like you are trying to predict a continuous number like price, salary, let's say hemoglobin count, it's like something like that, number of days that you would live on this planet, something like that, then it is a regression problem. So there are two kinds of problem. We can say one is classification. Let me write classification. The second one is regression, and classification is like target value is like categorical, and regression is like target value is like continuous. There are other categories to it, but let's just stick to it for now. And then So once that is done, so that's why we are calling it decision tree regressor, because we are ultimately trying to do a regression and then trying to predict a continuous variable, which is a number. Okay. So now what are the steps in building a model? Scikit-learn library is quite easy, simple, very standardized API. So first thing is you have to define what your model is. This is a step, you define what the model is. Okay, I want to define the model that I want to build. So what I want to build a decision tree regressor, and what goes inside this are called parameters. So these parameters will decide what type of decision tree regression you want. For example, now we are saying tree. So how many trees do you want? Like in this case, we are going to build, of course, only one tree. But if you use some other model like a forest, random forest, then you would probably say how many trees you want, like how long you want model to go, something like that. So these are parameters. This is a model. So that is defined. So the next thing is you're going to fit it. Fitting is nothing but the process of training it. So for example, if this is how your data is, fitting is nothing but putting a line, putting a decision boundary in such a way that the data points are separate. So if this is how your 2D data is, fitting is like this, making the model understand how to create or capture pattern, create a decision boundary. So that is what fitting is. So how better you fit is how good your model is. So how much you can train your model better is going to decide how better or good your prediction is going to be. So then after that, you're going to predict it on some data that the model has not seen before, and finally you're going to evaluate how the model looks like. So this is the typical workflow. So define the model, fit the data, training data with the model, so fit the model, and then predict it on the data that it has not seen, and then finally evaluate how the model is doing. So let's get started. So first step is we are going to import the model, the class that we want. So decision tree comes from the tree, so scikit-learn.tree, import decision tree regressor, define the model. So random state. Why do we want random state? Anytime you do something random inside a computer, it is always good to set a seed or random value, so that whenever you want to replicate this process, you get the same value. So random state is, you can set 1 1 1 1 1 1, whatever you want to do, you can set. And then the next thing is you have to fit the model. The first one is features, the second one is what you want to try to predict. So basically the model will learn that, oh, for these features, if these are the values, y values, so how am I going to fit the line? So that's what it is going to do. Because we are doing regression, it's basically trying to fit a straight line. Okay, so now let's run this thing. This process might take a little bit of time. Oh, y is not defined. That's a shame. I did not run it. Okay, go back, run this. Okay, so it says the decision tree model fitting is done at this point. So random state, we learned why do we need random state. Now that we have successfully fitted the model, we can start predicting. So let's make predictions for the following houses. Let's take this training, the same data. See, one thing that you might notice here is we are going to use the same data, but that is not going to happen in the real world, right? So you're not going to use the same training data to predict the model. So it's like, you know, teaching somebody numbers in such a way, then expecting them to believing that they know the numbers because they predicted using the same data. This is just for experimentation. In the next section, we're going to learn about model validation. So until that, just hold your horses. So make the prediction for the 5 houses. Let's see how the prediction looks like. So what is the prediction? So the prediction is, if this is your value, these are the values that we are predicting. Okay, so if you want to just check how the value, the actual value is, we can do, which is go to the actual data. Where is the actual data? We have Melbourne data. Then go back and do head. So you can see that number of rooms is 2, 3, 4, 3. So this is the same value. So if you want to see price, okay, I did not. So you can see what our model has predicted is, our model has almost exactly predicted whatever the reality. So this is what we predicted using the predict method. We predicted, and this is the original price. And now you might start celebrating, woohoo, I've got 100% accuracy. Probably every time you get 100% accuracy, you should be always skeptical, not celebrating, because most likely we have screwed up something, we have done something wrong, because we cannot do anything 100% accurate. That's a truth that we have to know. But very congratulations to you if you are at this stage, you have successfully predicted built your first machine learning model. So maybe that's a good thing. So let's go do model building exercise. Let me save this work. What is our model building exercise? So what is the exercise that we have got? Let's quickly look at it. Okay, so far you have loaded your data, reviewed it, the following code, run the cell to set up your environment where you left in the previous step. So we have training data, Iowa file path. We are going to read it and then we are going to set it up. Session is getting started. Set it up. Next step is step 1, specify the prediction target. So how do we want to call it? We want to call it using y. So y should be our prediction target. And what are we trying to predict? Before that we need to know what is the column. So we are going to predict something that is related to sales price. How do we know what is the column? Simply we go here and then do columns and then see if you can. Wow, there are so many columns. So now we need to figure out if there is anything related to price. Oh, there is something called sale price, and this is what we are going to predict. And what is the data frame name? This is the data frame. And to get this, I always like to copy and paste so that I don't mess up with the column name. That might take my time, and then I would start wondering what is wrong. So simple. We have got the prediction target. So next thing is, okay, I was supposed to add it here. That's bad. Okay, let's run it and check. Okay, correct. We have successfully done that. Now create the predictive features, create the explanatory variables which we are going to use. So what is the advice that they are giving? They are saying that we are going to use the following column names only. Okay, and like I said, I always like to copy paste it so that I don't mess up with the column name, because there is a very high chance that that the column name might be something else. Maybe what I'll do is I'll copy everything and then add it here, and then I would do this, 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 and I would do this, and then I need quote which I can select and give like this: quote, 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 quote. You can use double quotes as well. And then we are going to say what is the data frame name. Our data frame name is home underscore data dot, square bracket, because we are going to extract these column names and the column names. Then when we run it, correct, we have successfully got the feature names and extracted only those columns. You can quickly, okay, I think that is an extra assignment. You can quickly review it if you want. X dot head, you can see X dot tail, you can see, okay, all are good. So it looks good. So the next step is review the data before we move forward, and then try to see if everything is good. Let's take a quick look at the data. Prints the description statistics from this. So we'll do print of home X describe. So we got the description, that's good. Print the top few lines, that's what I think we did. We don't have to actually use print. In Jupyter notebooks there is an implicit print, so it works. We are good with this. We have reviewed the data. The next step is we have to specify the model, and then we have to run the model. And always, never, like, you don't have to always remember everything. Okay, so you think that you want to build a decision tree regression. So what you can do is, okay, I can go to Google and say scikit-learn decision tree regression. So you don't, the reason I'm saying this is you don't have to necessarily memorize it. You can go here and then see, okay, how do I do it? Is there an example? Yes, there is an example. You can copy this, come back here. Oops, this, okay. I have the first one, then I have to fit the model. How do I fit the model? I can okay, this is where I've defined the model, so I can do this. And then okay, random state, you can say random state is equal to 222, and then now we have to fit the model. So how do we fit the model? We say your model dot fit. We are not going to assign this to anything, that's something you have to remember. Like, once we have the model, we are going to say fit the model. And how are we going to fit the model? Okay, let's go and see the example. So we are going to, whenever we say fit, whenever we are going to fit, we are going to say okay, it is not defined here. Let me quickly show you dot fit. Okay, it's not here, so probably we have to see this, which is like, you can see x and y. So x and y, x and y. If you have given a different name when you created these objects, you should use the same name. Just remember that. Okay, correct. We have successfully fit the model, and then finally we can start making predictions. And how are we going to make the prediction? So we can use the model and then dot predict of, okay, what are we trying to make predictions for? Using x data, we want to predict for entire data. We have predicted. So usually at the end of this, it would give you the price. So whatever you have predicted, this is basically the price, the sale price. What is y, that is what you have predicted. And then think about the result. Use head method to compare top few predictions with this. So we can do that. So let's say this is our prediction. Okay, we have saved it to predictions, and predictions dot head. Oops, it's a numpy array, so we will not have head. So we can say 0 to 5 like this, and then we can say from our home data, can I see head, or I can basically say sale price and 0 5. So when we compare it, it is almost exactly same, no change. And the reason why, again, we have a 100% accuracy when we look at top 5 data is because we have used the same training data to also predict, which will never happen in the real world. So we successfully predicted, but you should always keep in mind that we will never hit 100%. So that takes us to the end of this exercise. And in the next section, oops, where is the next section? The next section we are going to learn about model validation. Now, what is validation? Okay, so you have built a model. Do you know how good is the model? Because that's the first question everybody is going to ask you. So if you're a data scientist working in a company and you tell your stakeholders that, hello, I've built a model, everybody is going to ask you, okay, how good it is. I think when you say model, you're going to tell them like model to predict sale price, but they'll ask you how good it is. Now, how are you going to evaluate? Evaluate is the keyword, or validate how the model, whether it is good. How are you going to evaluate the model? For that we have evaluation metrics. How are you going to validate whether the model is up to the quality, like model is of good quality? Because model validation will also help you iteratively improve the model. For example, one of the things that we saw when we did this is we said, okay, right now we'll use these 5 columns, 5 features, but we'll come back and start using more columns. Of course, more data, when we have more information for the model to learn, most likely it should improve the model performance, right? But how do you know whether the model is improved? If you do not know, you cannot iteratively improve the model. And that is where model validation as a concept come into the picture. So what is model validation? Model validation is nothing but a method for you to evaluate, measure the model quality. So in other words, you will evaluate, you will check whether the model's prediction, whatever you predicted, whatever like we finally eyeballed, is actually close to what happens in reality. So whether the actual value and the predicted value are close enough for it to be real. That's what model validation is going to do. And one of the huge mistakes that people do is, I think I've told multiple times, is that when you do prediction with your training data and then compare those prediction with your target values in training data, you will most likely see that you have got a good accuracy, and that is a big problem. It's a very big mistake. Why? Because you just use the same data that you trained your model, and then you're trying to predict that and then evaluate that, and then you're going to feel that, oh, I did correct prediction, because it's wrong. Why is it wrong is what we are going to see in this section. So let us compare. Let us compare let us come up with a metric. So we are going to use a metric that will help us evaluate the model. So these are like family of metrics. These are called evaluation metrics. And in the previous slightly sometime back, I told you about classification and regression. Based on what kind of machine learning problem that you are trying to solve, this evaluation metric might differ, might change. So if it is a regression, you might use a different evaluation metric. If it is a classification, you might use a lot of different metrics. So every time the metric might change. So now what are we going to do? That we want a metric that will help us compare our predicted value and actual value, and then figure out how are our predictions, whether it is good or bad. Okay, so that's what we are going to do. So now for that we are going to settle with a metric called mean absolute error, MAE. Mean absolute error is quite a useful metric if you are doing time series. Just keep it in your back of your mind. Whenever you do time series forecasting in the future, mean absolute error would always come most likely. So what is mean absolute error? Just dissect this. First we are trying to calculate the error, and then we are trying to calculate the absolute error, which means without any sign. What is an error? Actual value minus predicted value. Let us assume that the actual cost is $150,000 and what we predicted is $100,000. The mistake, the error that we made is $50,000. We made an error of $50,000. Okay, so that is our error. But what if it is minus $50,000? And that's why we do absolute. So we just take the absolute value so that everything is like a positive value. And then what is mean? So of all the predictions we made, we are going to calculate what is the average error value. So now you have got all the errors absoluted, and then finally make the average of it. So basically in simple English, on an average, our predictions are off by X. So let us assume that you have got 10 predictions. Of the 10 predictions, every prediction has like $50,000 is your error. So now your absolute error, mean absolute error is, let's say, $50,000. So 50,000 would be your mean absolute error for you to know, because you have made an absolute error of $50,000. So this will help us understand how much our predictions are off from the actual value using the current set of features and the current model that we have built. So two things can influence your model predictions quality. One is X, what you use to predict. Second is what model in fact you used. Did you use any model that cannot learn this kind of complex data structure, or did you use a complicated model that might have there is a word called overfitting. I used it by mistake at this point, but you will learn it slightly in the future. Okay, so first to check MAE, mean absolute error, which is also something you don't have to do it manually. Thanks to scikit-learn.metrics, sklearn.metrics, you can import mean underscore absolute underscore error, which will give us mean absolute error. And now because we have already predicted, so when you say Melbourne underscore model, which is the model that we built, and then predict, this is our price, predicted price. So we have Y, actual values, we have predicted values. When you use mean absolute error and then compare these two, we get a value of 434. So we are in usually about $434 off, which seems like a good price, right? Means if I am predicting a house price for like $10,000, $12,000, $13,000, if I make a margin of error of like $434, I should be a very good predictor. Like I've done a great job. So now before you think that you as a data scientist or me as a data scientist, we have done a great job, there is a problem. And what is the problem? The problem is with in-sample scores. What do we mean by in-sample score? What do we mean by in-sample score is we use the same sample of houses to build the model and also to evaluate the model. So same data, training data, sample of data that we use to build the model, we also use to evaluate the model, and here is why it is bad. Now imagine there is a large real estate market and there is an attribute, there is a feature where the door color, basically let's say door color has nothing to do with home price. Okay, so door color has nothing to do with home price, but coincidentally or accidentally, the data that you used, only the data that you used, this is like accidentally, the data that you used has got all the green doors are expensive. Whenever it is green door, it is expensive. Whenever it is not green door, it is not expensive. This is not how the market works, but accidentally you got a data like this in the sample. Now what will happen is when you build a model to predict home prices, now the model, the machine learning model, which is nothing but like a mathematical equation, like slightly more than mathematical equation, but let us assume at this point that it's like a mathematical equation. So now it is going to think, oh, what I learned from this model is, this training data is, having a door color of green is one of the important features that will help me predict the house price. So it's going to use that as an important feature to predict the house price. Now when we use this with our validation data, which has like all colors of door, so where this logic or this stupid logic or insane logic of green color door has nothing to do with house price. Now imagine what's going to happen. Our model that we built using the small sample of data, which is our training data, which has this bias towards green door, when we go to the real world, which is like the data outside our training data, which is like out of our sample, is our model is going to be very poor. It's going to be extremely inaccurate when we use it in practice. And that is why there is a concept called validation data. So the concept of validation data is to build model. So you have the existing data, sample of houses, you split this data into two or multiple ways, like, okay, there are different strategies. You split this data into training data and validation data. So every time you build a model with your training data, you can actually validate against the validation data, so that when you go to the real world where you have not seen any data, your model performs better, not poor. So to make sure that your model performs better in the real world, you need to have validation data that you are going to validate against every time you build a model with your training data, which is going to be a subsample. A sub selection of sample from the original training data that you got is going to be your training data and your model validation data, and you're going to compare it with your evaluation metric. That's what basically we are going to do. That's what called model validation or cross validation. Anytime you hear the word CV, cross validation, model validation, validation techniques, this is what basically it means. And this, I don't know if they have introduced the word, but there is a very nice word called overfitting. Overfitting. So now what is overfitting? Overfitting is nothing but you use a machine learning model that will try to learn as much as possible. Now the green door being expensive, like the houses with green door being expensive, is one random accidental thing, has nothing to do with house prices in real life. But what your model might think that it's a signal, but it is actually a noise. So when your model learns a noise as a signal while you are doing the model training, you know that it's going to perform very poorly in the real world data, but it might do well in your training data. So this process is called overfitting, where the model tries to fit slightly too much than what is required, because it tries to consider a noise as signal. So this is called overfitting. Just read more about overfitting. There are a lot of good explanations on the internet that would explain you what is overfitting. So now let's code the model validation thing. So again, you don't have to do anything manually. Thanks to scikit-learn, you have got a scale-learn.model selection, and then you can do train underscore test underscore split. So whatever we said validation, that is what we are going to do, train underscore test underscore split. It's going to be called test data. You can call it whatever you want. So when we do that, we have X, we have Y, and then we are going to split both, and then we are going to use a random state, and we are going to say train X and validate X, train Y and validate Y, and you can see that how tuple is playing a role in this thing. So when we split this thing, it's going to output 4 different objects, like call variable values, and we capture everything in one expression. So now we are going to do a simple decision tree regression, and then we are going to fit the model, and then we are going to use only train X and train Y, because we want to validate this model Melbourne underscore model against this validation data val underscore X and val underscore Y. So after we have this, we are going to predict it whatever we, because we are not going to predict it with our training data, because that is insane, right? That's what we learned until now. So we are going to predict it against our validation data and then compare these two predictions. And what you see, like it's like a BuzzFeed article, what you see might something you might not believe. It's an absolute shocker, because within our training data, the error was somewhere around $434. But when you actually compare it with the data that the model has not seen, even though it is the same sample, if the data that the model has not seen, our error, mean absolute error, is around $261,000, which means our model, the process in which we build the model, we have overfitted the model. And that is absolutely insane, because if we had gone to the market with this model, imagine now housing prices is fine, nobody's life is going to get impacted with housing prices, but what if you are going to predict whether somebody has cancer or not? What if you are going to predict whether an email is spam or not? What if you are going to predict somebody's credit score? If you screw up any of these things, the impact is huge. That's why model validation is extremely important. So anytime you learn about data science, as much as you learn about model building, you should learn about cross validation strategies. The more cross validation strategies you know, the better cross validation strategy that you have got. Cross validation is like model validation strategy that you have got, the better your model or robust your model is, so you can do better. On Kaggle, if you ever get into Kaggle competition, let's see if during the course of this course there is a private leaderboard and public leaderboard. A lot of times you would see like some model doing great in public leaderboard, but it has ended up overfitting. So on the private leaderboard it would come down a lot, so it's usually called as like model leaderboard shakeup. So if you don't want to get into any of those things, no, model validation is quite important for you. I think I've given a lot of explanation on this thing. Let us get started with the exercise. I'm just doing a couple of exercises, but these days I don't want to do exercise so that you can do it yourself. So at this point it's a good point for you to stop this video and then do the exercise yourself. So let's load the data set that we have. Just run this thing. What are we running? We are basically building the importing pandas, importing decision tree regression, again like reading the training data and then extracting y, selecting the feature columns. This is the same model that we built in the last exercise, and then extracting the feature columns and then using decision tree regressor and fitting the model. And then once we have that, we are going to calculate. Okay, so right now this is where we have a model called Iowa model. We have actual variables, and then we see we are almost same. So now let us try to split training and test. How are we going to do that? We are going to simply, like I always say, if you do not know how to do that, just go back and then say scikit-learn split training and test data. When you do that, you would get this. So you can go to the example and then just copy. So this is the easiest way for not making mistake. Where am I? Okay, here. So paste this. At this point we have the function. Now we have to just fill in this comment, which is train this thing. So we are going to get this, put it here, and then x, y, and whenever we deal with the random thing, we are going to say random state is equal to 222, and then run this. Oops, training data had different rows than expected. Did I do something wrong? So recall your features are loaded into data frame x and y. This is here, this thing. Let's quickly see x and y, and okay, we didn't define the test size. Train x to have shape. Your code produced train x with the shape. Okay, I think, did they say, okay, we have to give random state 1. That's some. This is what happens when you don't read instructions, like me. Random state 1. You can of course define all those things, but yeah, I didn't read it properly, so just say random state 1, so they know that what kind of data you would get, so they validate it. That's completely fine. Okay, so the next thing is create a decision tree regressor and set the model state again 1. Okay, so decision tree regressor, random state is equal to 1, and fit the model on training data. Iowa model dot fit, and what are we going to fit on? We are going to fit on train of x comma train of y. This is what we are going to fit. Okay, correct, we have successfully fitted. And then the next step is make predictions with validation data. What are we going to make predictions? sorry, I have a model dot predict and validation val x is what we're going to predict on, because we are doing validation. This is correct. And then the next thing is print few top validation val predictions 5, and what do we want to do? The few actual prices from validation data. How do we know actual prices? Val y 5. Oops. Okay, so we see 1850, we are off by almost like $50,000 here. Second is we are off less than $10,000. Third one is again $10,000, again around $10,000, and the fourth one is again $20,000. So we are on the average, like you can see, like we are off about like 20,000, 10,000, somewhere 50,000. So now how do you know? Like we eyeballed it, we know that this is wrong, but how do you know how much we are different? That's why we need evaluation metric and validation. We are going to calculate the evaluation metric, which in this case is mean absolute error. So what we are going to do is mean absolute error of what we predicted, what is actual. You can see that, oh, we didn't print it, I'm sorry. You can see we are off about like approximately $30,000, and that's what we almost eyeballed it, but we can see. And is that MAE good? It doesn't look good. Means if you are going to be off about like $30,000 for a house price, which almost ranges in like 180,000, 130,000. So I don't think that seems good, but yeah, that's what we are going to learn in the future sections. But there is no general rule, but you know the domain that you are, so you know how a good broker might predict, and now you can compare that good broker with your data science model to understand. Fortunately the next section is about underfitting and overfitting. So see you tomorrow. If you have any comments, please let me know in the comment section. Otherwise, I hope that this video was helpful to you. Stay safe. Happy coding.